Step outside tonight and look up. Find Jupiter. It won't be hard. It's one of the brightest objects in the night sky. A steady, cream-white point of light that doesn't flicker the way stars do. It just sits there, patient, unchanging, like it's been waiting. Most people see it and feel nothing. A planet. Our neighbor. Part of the furniture of the solar system we grew up learning about in school. But here's what they don't teach you. The Jupiter you're looking at right now, that calm, distant light, is the wrong size. It is smaller than it should be. And that difference, that gap between what Jupiter is and what it almost became, is the reason you exist. Not metaphorically, not philosophically, literally. If Jupiter had been slightly larger during the formation of this solar system, not twice as large, not 10 times, slightly, the chain of events that produced Earth, that produced life, that produced every human being who has ever lived would never have happened. By the end of this video, you will understand exactly how close that was, and you will never look at that light in the sky the same way again. Let's start with the basics, because the word planet doesn't do Jupiter justice. It doesn't even come close. Jupiter is not a planet the way Earth is a planet. Earth is a rocky world with a surface you can stand on, oceans you can sail across, an atmosphere thin enough to see through. Jupiter is none of those things. Jupiter is a world of gas and liquid so massive that it warps our intuitions about what a planet can even be. Its diameter is 11 times wider than Earth's, but diameter is a flat number. It doesn't capture volume. By volume, you could fit 1,321 Earths inside Jupiter. Stack them however you want. They all fit, with room to spare. Its mass is more staggering still. Jupiter weighs 318 times more than Earth. More than that, Jupiter is 2.5 times more massive than every other planet in the solar system combined. Saturn, Uranus, Neptune, Mars, Venus, Mercury, Earth, add them all together. Jupiter outweighs all of it twice over. Think about what that means for a moment. Our solar system has 8 planets. One of them accounts for the vast majority of all planetary mass in the entire system. The other 7 are almost an afterthought. But here's where it gets genuinely unsettling. Jupiter is not just big for a planet. Jupiter is big for something that isn't a star. The boundary between a gas giant and a star is not arbitrary. Stars fuse hydrogen in their cores. That's what makes them shine. To ignite that fusion, you need enough mass to generate enough pressure at the center to force hydrogen atoms together. The minimum mass for that process is roughly 80 times the mass of Jupiter. Jupiter sits at about 1/1000th the mass of our Sun. It is not close to that threshold by any conventional measure. But here's the part that should stop you cold. Jupiter is not the only size it could have been. In the early solar system, in the chaos of formation when gas and dust were still swirling and clumping and colliding, Jupiter could have grown larger. The raw material was there. The conditions allowed for it. Models of planetary formation show that gas giants in young solar systems can undergo what's called runaway accretion, a feedback loop where the planet's growing gravity attracts more gas, which increases the gravity, which attracts more gas, which increases the gravity, accelerating without limit until something stops it. Something stopped Jupiter. We are not entirely sure what. The leading theory involves the formation of Saturn, another giant pulling material away from Jupiter's feeding zone, cutting off the supply. The sun's radiation also played a role, gradually clearing the gas disk that Jupiter was feeding on. But the stopping was not guaranteed. It was not written into the physics. It was contingent. It depended on timing, on position, on the behavior of other forming bodies in a chaotic, violent, barely structured infant solar system. Jupiter stopped at 318 Earth masses. It could have kept going, and if it had kept going, if it had accumulated just enough additional mass to cross certain thresholds, the history of this solar system would have taken a completely different path. Not a better path, not a worse path. A path with no Earth on it. Here's the scenario that keeps planetary scientists up at night. It doesn't require Jupiter to become a star. It doesn't require anything dramatic. It just requires Jupiter to be somewhat larger than it is. And by somewhat, we mean in the range of 13 times its current mass. At roughly 13 Jupiter masses, something changes. The object stops being a planet and starts being what astronomers call a brown dwarf, a failed star, a body massive enough to briefly fuse deuterium in its core to glow with a dim reddish heat, but not quite massive enough to sustain the full hydrogen fusion of a true star. A brown dwarf Jupiter would not have been visible the way our sun is visible. It would not have lit up the sky. But it would have radiated heat. It would have generated its own gravity field of a categorically different magnitude, and it would have fundamentally altered every orbit in the inner solar system. But let's not even go that far. Let's stay well below the brown dwarf threshold. Let's say Jupiter simply grew to 5 times its current mass. Still a gas giant. Still a planet by most definitions, but 5 times more massive. The consequences would have cascaded outward from Jupiter's orbit like a shockwave through everything inside it. Jupiter's gravitational influence scales with its mass. A Jupiter 5 times heavier doesn't just exert 5 times more gravitational pull, it reaches further, it perturbs more, it controls more of the orbital architecture of the solar system. Objects that currently follow stable orbits in the asteroid belt, objects that were gently nudged and sorted by Jupiter's current gravity, would instead have been violently scattered. The asteroid belt as we know it would not exist. What would exist instead is a far more chaotic region of the solar system.
After helping hundreds of people improve their sleep, I created a simple guide that shows the habits and techniques that can help you sleep more deeply. Click the link pinned in the comments to get the guide.
With debris crossing the orbits of the inner planets on regular, unpredictable timescales. But there's something worse. The inner solar system's architecture, the spacing of the rocky planets, the specific orbital positions of Mercury, Venus, Earth, and Mars, is not random. It emerged from the gravitational sorting that happened over hundreds of millions of years. A slightly larger Jupiter would have participated in that sorting differently. The resonances it established, the orbital paths it carved, the debris it cleared or deflected, all of it would have been different. Different enough that Earth, as a stable rocky world in the habitable zone of the Sun, may never have formed at all. Not destroyed, not removed, never assembled in the first place. The material that became Earth, the rock and metal and ice that slowly clumped and merged and collided over tens of millions of years, would have been scattered, sent on chaotic orbits, collided too hard or not hard enough, flung into the sun or thrown out past Neptune into the cold. Earth is not inevitable. It was built by a process that required specific conditions. A slightly larger Jupiter would have made those conditions impossible. Let's pause here, because I want to be precise about what I'm saying. I am not saying Jupiter is the only reason Earth exists. The story of Earth's formation is complicated. It involves the Sun's exact properties, the distance of the solar system from the center of the galaxy, the timing of the solar system's formation relative to nearby supernova events, and dozens of other factors. But Jupiter is one of the hinges, one of the critical variables. And unlike some of those other factors, Jupiter's mass was not fixed by physics. It was determined by the chaotic, contingent dynamics of the early solar system. It could have been different. It was almost different. Here's something most people don't know about Jupiter. It didn't form where it is now. Jupiter formed further out in the solar system, beyond what's called the frost line, the distance from the sun where temperatures are cold enough for water and other volatile compounds to freeze into solid ice. That ice was critical. It gave Jupiter's forming core the solid material it needed to grow quickly, to reach the mass threshold where it could begin pulling in gas from the surrounding disk to trigger the runaway accretion that made it the giant it is. But then Jupiter moved. This is called the Grand Tack hypothesis, and it's one of the most important and dramatic stories in planetary science. The theory proposes that Jupiter, after reaching roughly its current mass, began migrating inward, not slowly drifting, actively spiraling toward the sun, driven by interactions with the gas disk it was embedded in. Jupiter moved inward until it was approximately where Mars is today. Think about that. The largest planet in the solar system? A world that could contain 1,300 Earths, traveling inward through the region that was then occupied by the nascent building blocks of the rocky planets. Rocky planets that had not yet formed. Raw material that was still in the process of assembling itself. Jupiter's passage through the inner solar system was not gentle. It scattered debris. It cleared entire regions. It gravitationally ejected planetesimals, rocky bodies that could have grown into planets, sending them into the sun or out into deep space. The material that would have built a larger Mars, a fourth or fifth rocky planet in the inner system, was swept up or scattered by Jupiter's passage. This is why Mars is small. Mars is the runt of the inner solar system, not because it formed in a bad location, but because Jupiter ate its lunch. The material that should have built Mars into an Earth-sized planet was stolen, scattered, destroyed before it could be incorporated. And then Saturn formed. Saturn's formation changed the gravitational equation. The two giants entered into an orbital resonance, a gravitational lock where their orbital periods fell into a simple ratio, and that resonance reversed Jupiter's inward migration. Jupiter stopped. It began moving outward again. The Grand Tack, named for the sailing maneuver where a ship reverses course, was complete. Jupiter retreated to roughly its current position. The inner solar system was left scarred, depleted, but not destroyed. What remained of the rocky material continued assembling. Earth formed, Mars formed, smaller than it should have been. The asteroid belt, the debris Jupiter left behind, the rubble of planets that never got the chance to become planets, settled into the region between Mars and Jupiter. This is why the asteroid belt exists. It is not the remains of a destroyed planet, as old myths suggested. It is the remains of a planet that was never allowed to be born. But here is the part that should disturb you. The Grand Tack, Jupiter's inward migration and retreat, depended on Saturn forming at the right time and in the right place. If Saturn had formed later, if Jupiter had migrated further inward before being pulled back, the inner solar system's architecture would have been even more thoroughly disrupted. The material available to build Earth would have been further depleted. The orbits would have been less stable. Saturn saved Earth from Jupiter. We owe our existence not just to Jupiter being the right size, but to the timing of Saturn's formation and to the gravitational resonance between two giants that neither of them chose to enter. The solar system is an extraordinarily lucky place. You may have heard this one before. Jupiter is Earth's shield, the great protector, a gravitational bodyguard positioned in the outer solar system, sweeping up comets and asteroids before they can threaten the inner planets. It's a comforting story. It's also wrong, or at least profoundly incomplete. Jupiter does intercept objects. In 1994, we watched it happen in real time. Comet Shoemaker-Levy 9 was captured by Jupiter's gravity, torn into 21 fragments, and then, over the course of 6 days, each fragment slammed into Jupiter's atmosphere at 60 kilometers per second. The impacts left scars in Jupiter's cloud tops larger than the diameter of Earth. The energy released was equivalent to hundreds of millions of nuclear warheads. If that comet had found its way to Earth instead, extinction. So yes, Jupiter intercepts objects. Jupiter absorbs impacts that might otherwise threaten the inner solar system. That part is real. But here's the catch that the textbooks leave out. Jupiter doesn't just absorb objects, it also launches them. Jupiter's gravity is a scattering mechanism, not just a collection mechanism. When a comet or asteroid passes too close to Jupiter without being captured, it doesn't simply continue on its original path. It gets deflected, sometimes outward toward the outer solar system or interstellar space, sometimes inward toward the Sun, toward the rocky planets, toward Earth. Jupiter throws things at us, the long-period comets, the icy visitors from the outer solar system that swing through the inner planets on orbits that take thousands or millions of years. Many of them owe their current trajectories to gravitational encounters with Jupiter. Jupiter pulled them out of stable orbits in the Kuiper belt or Oort cloud and redirected them inward. Some of those comets struck Earth in the distant past. Some of them may strike Earth in the future. The scientific debate about whether Jupiter is a net protector or a net threat is genuinely unresolved. Some models suggest that a solar system without Jupiter would actually see fewer large impactors reaching Earth because there would be no giant planet redirecting distant debris.
After helping hundreds of people improve their sleep, I created a simple guide that shows the habits and techniques that can help you sleep more deeply. Click the link pinned in the comments to get the guide.
Inward. Other models support the traditional shield hypothesis. The truth is probably somewhere in between. Jupiter giveth, and Jupiter taketh away. But here's what's not debated. A larger Jupiter, a Jupiter that had accumulated more mass during its formation, would have been a far more active scatterer. Its gravitational reach would have extended deeper into the inner solar system. The probability of redirecting objects toward Earth would have been higher. The orbital stability of Earth itself, the slight eccentricity of our path around the Sun, the tilt of our axis, the long-term regularity of our seasons, all of it is influenced by Jupiter's gravity. A more massive Jupiter would have pushed and pulled on Earth's orbit differently. It might have been enough to kick Earth out of the habitable zone periodically, not to destroy Earth, but to make it uninhabitable, to trigger ice ages severe enough to sterilize the surface, to destabilize the climate so thoroughly that complex life never got a foothold. A slightly larger Jupiter, same solar system, no complex life. Let's talk about the habitable zone, because it's smaller than most people realize. The habitable zone around our Sun, the band of distances where liquid water can exist on a planet's surface, where temperatures are neither too hot nor too cold for the chemistry of life, extends from roughly 0.95 astronomical units to about 1.37 astronomical units from the Sun. Earth orbits at 1.0 astronomical units. We are not in the center of the habitable zone. We are not comfortably nested inside it with plenty of room on either side. We are toward the inner edge. We are not far from the zone where the greenhouse effect runs away, where oceans boil, where Venus-like conditions take hold. Venus, for reference, orbits at 0.72 astronomical units. It is a world of crushing atmospheric pressure and surface temperatures hot enough to melt lead. It is what happens when a rocky planet sits just a bit too close to the Sun, just a bit too far inside the habitable zone. Earth's position, 1.0 astronomical units, liquid oceans, stable climate, is not guaranteed by physics. It emerged from the accretion process. It depends on how much material was available to build Earth at that specific distance. And how much material was available and what kinds of impacts Earth experienced during its formation was influenced by Jupiter. A slightly larger Jupiter would have altered the distribution of material in the inner solar system during the accretion phase. Earth might have formed slightly different in composition. More or less water, more or less volatile elements. It might have formed at a slightly different distance from the Sun. It might have experienced different giant impacts during its formation, impacts like the one that is thought to have created the Moon, a collision between proto-Earth and a Mars-sized body called Theia. The Moon matters. The Moon's gravitational influence stabilizes Earth's axial tilt, the tilt of our planet relative to its orbital plane. Without the Moon, Earth's axial tilt would vary chaotically over astronomical time, swinging from near zero to extreme values. That instability would have severe consequences for climate, for seasons, for the long-term habitability of the surface. The Moon exists because of a specific giant impact during Earth's formation. That impact happened because of specific dynamics during the accretion phase. Those dynamics were shaped by Jupiter. Everything connects. A slightly larger Jupiter. No specific impact at the right angle. No Moon. Unstable axial tilt. Climate chaos. No complex life. Or a slightly larger Jupiter. Inner solar system depleted of material. Earth forms smaller, drier, with less geological activity. No plate tectonics. No carbon cycle. No regulation of atmospheric carbon dioxide. Temperature spirals. Life, if it begins, doesn't survive. The number of paths from slightly larger Jupiter to no Earth as we know it is not one. It is not three. It is a branching tree of consequences, each branch leading away from everything that exists. We are not unique in having a giant planet. In the last 3 decades, astronomers have discovered thousands of exoplanets, planets orbiting other stars. And among the most common types of planets we find are gas giants, massive worlds of hydrogen and helium orbiting their stars in a vast range of configurations. But here's what we've learned from studying those systems. Many of them have hot Jupiters, gas giants that orbit extremely close to their stars, closer than Mercury orbits our Sun. These planets almost certainly didn't form where they orbit now. They formed in the outer system, then migrated inward, driven by interactions with the gas disk until they were baking in the heat of their star. When a Jupiter-mass planet migrates through an inner solar system, it doesn't leave it intact. It scatters the rocky material. It ejects it, consumes it, redirects it. What's left is a devastated inner system with no Earth-like planets. Those solar systems, and we have found many of them, are probably empty of habitable worlds. The giant came in too close. The rocky planets that might have been are gone. Our solar system avoided this fate. Jupiter migrated inward during the Grand Tack. Yes, but it stopped at Mars' current orbit. It didn't come all the way in. It retreated. The inner system was damaged, not destroyed. Why did our Jupiter stop where it stopped? Because Saturn formed in time to pull it back. Because the timing worked. Because this specific solar system, in this specific galaxy, at this specific moment in cosmic history, had the right configuration. And here's the number that should stop you completely. Astronomers estimate that between 10% and 20% of Sun-like stars host a Jupiter-mass planet in an orbit similar to our Jupiter, far enough out in the right configuration to possibly play the same architectural role that our Jupiter plays. 10% to 20%. That sounds like a lot. Our galaxy has hundreds of billions of stars. If 10% of them have a correctly positioned giant planet, that's tens of billions of solar systems that might have the basic prerequisite for stable rocky planets in their inner systems. But the full chain of requirements is longer than just having a Jupiter. You need a Jupiter of the right mass. You need it to have migrated the right amount. You need a Saturn to pull it back. You need the timing to be right. You need the inner solar system material to be available. You need the specific impact history that produces a moon. You need the moon to be the right size and distance to stabilize the axial tilt. Each of those requirements narrows the number of systems that qualify. We don't know by how much. We don't have enough data on enough solar systems to calculate the odds precisely. But every additional requirement we add to the list makes the number smaller. Earth may be common. Earth may be extraordinarily rare, we don't know. And that uncertainty, sitting in the gap between common and rare, is one of the most important unanswered questions in all of science. Let's return to Jupiter. The real one, the one orbiting our Sun right now at 5.2 astronomical units, sweeping through its 12-year orbit, maintaining the gravitational architecture of this solar system with a mass that is exactly what it is. Not what it almost was. What it is. 318 times the mass of Earth. Massive enough to shape the inner solar system. Not so massive as to destroy it. That line, the line between what Jupiter is and what it almost became, is not a wide line. In the context of what was possible during the formation of this solar system, the difference between a Jupiter that allows Earth and a Jupiter that prevents Earth is not an enormous gulf. It is a narrow margin. Scientists working on planet formation models have put rough numbers to this. Studies of solar system analogs suggest that Jupiter needed to stop its inward migration before crossing approximately 1.5 astronomical units, before getting too close to the zone where Earth's building blocks were accumulating. If Jupiter had migrated even a little further, the material available to build Earth would have been insufficient. Jupiter stopped at roughly 1.5 astronomical units during the Grand Tack. It came within the margin. It stopped just in time. Think about what that means. 4.5 billion years ago, in a disk of gas and dust around a young sun, a planet that would become Jupiter was growing and moving. Elsewhere in that same disk, the raw material of Earth was beginning to accumulate. The outcome, whether Earth would exist, whether the ingredients for life would come together, whether 4 billion years of evolution would eventually produce a species capable of asking these questions, depended on when Jupiter stopped moving. Jupiter stopped. And then you were born. Step outside tonight. Find that steady light in the sky. You know what it is now. Not just a planet. Not just our neighbor. A gravitational anchor that has been holding the inner solar system in place for 4.5 billion years. A giant that migrated toward the sun and was pulled back just in time. A world whose exact mass, not larger, not smaller, exactly what it is one of the conditions that made your existence possible. Jupiter has been out there the entire time, through every extinction event that has struck this planet. Through the asteroid impacts, the ice ages, the supervolcano eruptions, the 5 mass extinctions that nearly erased complex life from Earth's surface. Through all of it, Jupiter has been completing its 12-year orbit. Pulling, stabilizing, deflecting, absorbing. It was there before the first cell divided in some ancient ocean. It was there before the first fish crawled onto land. It was there before the first human looked up at the night sky and wondered what those lights were. And it will be there long after. The solar system is not a machine designed for human survival. It is not arranged with us in mind. It is the product of chaos and physics and accident, of giant planets migrating and stopping and resonating, of impacts and scatterings and improbable timings stretching across billions of years. But somehow, in all of that chaos, the numbers worked. Jupiter is the right size. It stopped in the right place. Saturn formed at the right time, the material assembled correctly, the impacts happened at the right angles. The moon formed. The axial tilt stabilized. The climate held, and here you are. Not because the universe built a place for you, because the universe, in 4.5 billion years of violence and chaos, accidentally made one. If you found a new perspective in this video, subscribe, and I'll see you next time. Scientists who model planetary formation use a specific term for what almost happened to Jupiter. They call it runaway gas accretion, and it is exactly as unstable and alarming as it sounds. When a young planet's core grows past a critical threshold, somewhere between 10 and 15 Earth masses, something changes in its relationship with the surrounding gas disk. Below that threshold, the planet accretes gas slowly, almost passively, pulling in whatever wanders close enough. Above it, the planet's gravity becomes strong enough to actively compress the gas envelope surrounding it, which generates heat, which reduces pressure at the boundary, which allows more gas to fall inward, which strengthens the gravity further. It becomes a self-sustaining loop. The planet stops growing at a set rate and starts growing exponentially. Models show that during runaway accretion, a young gas giant can double its mass multiple times within a relatively short period. In astronomical terms, fast. Millions of years, not billions. Jupiter went through this phase. This is how it became the giant it is. The runaway accretion consumed the available gas in its feeding zone, and then the gas disk around the young sun dissipated, blown away by the sun's increasing radiation, and the feeding stopped. The timing of that dissipation was not predetermined. Gas disks around young stars last for different amounts of time, anywhere from 1 million to 10 million years, depending on the star's mass, the density of the surrounding cloud it formed from, and other factors. Our sun's disk dissipated at roughly 3 to 5 million years after the sun formed. If that disk had lasted another million years, Jupiter would have had another million years of runaway accretion to work with. A million years of runaway accretion is not a trivial amount of additional mass. It could have added tens of Earth masses. It could have pushed Jupiter toward or past that 13 Jupiter mass threshold into brown dwarf territory. 1 million more years. The gas disk of our solar system dissipated at a moment that was close enough to Jupiter's runaway accretion phase that the margin between our Jupiter and a Jupiter too large for Earth was, in cosmic terms, narrow. And here's the part that cannot be stressed enough. That dissipation timing was not designed. It was not calculated. It emerged from the specific properties of the molecular cloud that collapsed to form our solar system, from the mass and rotation of that cloud, from the density of gas in the region of...
After helping hundreds of people improve their sleep, I created a simple guide that shows the habits and techniques that can help you sleep more deeply. Click the link pinned in the comments to get the guide.
The galaxy where our sun formed 4.5 billion years ago. Conditions that existed before any of this existed. Before the sun, before the planets, before Earth, before life. The timer was set before there was anything here to benefit from when it stopped. There is one more piece of this story that most documentaries skip over, and it involves the ingredient that may be the most critical of all. Water. Earth is a water world. 71% of the surface is covered by ocean. That water is not just scenery, it is the medium in which life began, the solvent in which the chemistry of cells operates, the buffer that moderates climate, the carrier that distributes heat and nutrients across the planet. Where did Earth's water come from? This is not a settled question, but the leading hypothesis points outward, past the frost line, into the region where water ice could exist as solid material, into the zone where Jupiter formed. The early inner solar system was hot. At the distance where Earth formed, water could not exist in solid form. It was too close to the sun. The raw material that assembled into Earth was dry rock and metal. Dry. The water arrived later, delivered by impacts, by comets and asteroids from the outer solar system that were deflected inward, by Jupiter, into trajectories that crossed Earth's orbit during the late heavy bombardment, a period roughly 4 billion years ago when the inner solar system was bombarded by an intense flux of debris from the outer system. Jupiter caused that bombardment. Jupiter's gravitational interactions with the outer solar system, including interactions with Neptune and Uranus that sent those planets on their own migrations, destabilized a vast reservoir of icy bodies. Many of those bodies were flung inward. Many of them struck Earth. They brought water. Without Jupiter's influence on the outer solar system, the late heavy bombardment may not have occurred. Or it may have been weaker, delivering less water. Or the timing may have been different. Too early before Earth had cooled enough to retain water, or too late after life had already begun and the impacts would have been catastrophic rather than generative. The water in your body, the water in every ocean and river and lake on this planet, is there because Jupiter flung icy debris from the outer solar system inward at the right time. A different Jupiter, more massive, less massive, in a different orbit, might have delivered too much water, drowning any continental land masses and producing an ocean world with no geology and no complex life. Or too little water, leaving a dry Mars-like planet where the chemistry of life cannot get started. Jupiter calibrated the water delivery. Not intentionally, not intelligently, but with a precision that, in retrospect, looks almost designed. It was not designed. That's the point. That's the thing that is almost impossible to sit with. All of this, the water in your blood, the oceans outside your window, the life that has evolved and diversified and produced consciousness on this planet, all of it rests on a series of contingent events. Events that required Jupiter to be the size it is. Events that required the gas disk to dissipate when it did. Events that required Saturn to form when it did, and pull Jupiter back when it did, and deliver the water when it did. None of it was guaranteed. All of it happened. And you are the result. Which brings us to a question that sits at the edge of everything we've been discussing. If Jupiter's exact configuration was necessary for Earth, and if that configuration depended on a chain of contingent events, the right disk dissipation timing, the right Grand Tack distance, the right Saturn formation moment, then how common is the right configuration across the galaxy? We have now found thousands of exoplanets. We have characterized dozens of solar systems well enough to map their giant planet architecture. And what we have found is this: solar systems like ours are not the norm. Most solar systems with giant planets look nothing like ours. Many have hot Jupiters, gas giants orbiting so close to their stars that a year lasts only a few Earth days. Some have multiple gas giants in the inner system, chaotically interacting. Some have no giant planets at all, which means no gravitational shepherding of the inner system, no late heavy bombardment, probably no water delivery in the right quantities. The fraction of solar systems that have a gas giant in an outer, stable orbit, far enough out to play the role Jupiter plays, is somewhere between 10% and 20% of Sun-like stars. Maybe. The data is still incomplete. And within that fraction, the number that have a Jupiter with the right mass in the right orbital position with the right migration history is smaller still. We cannot calculate the exact number because we don't have enough data. But every planetary scientist who works on habitability knows that the number shrinks each time you add another requirement. There is a concept in astrobiology called the rare Earth hypothesis. It proposes that the conditions necessary for complex life, not microbial life, not simple chemistry, But the complex multicellular organisms that eventually produce intelligence are so specific and depend on such a long chain of contingent events that complex life may be extremely rare in the universe. Jupiter is one of the central exhibits in the case for rare Earth. Not because Jupiter is unusual in existing, gas giants are common, but because Jupiter is unusual in being exactly what it needs to be, in exactly the right place, having done exactly what it needed to do during the formation of this solar system, at exactly the right time. That is not common. That may be extraordinarily uncommon. We don't know. And the silence from the rest of the universe, the fact that in 60 years of listening with our most sensitive radio telescopes, we have not heard a single signal that was not generated by natural phenomena, may be telling us something. It may be telling us that the chain is long, that Jupiter being right is one of many links, that most solar systems get one of those links wrong, and that wrong link is enough to prevent the emergence of a species capable of asking the question. Or we may simply have not listened long enough. Or in the right direction. Or with the right instruments. We don't know. But we know this. You are here. And the gas giant hanging in your night sky, the one that looks like a steady, patient point of light, is part of why. Not the whole story, not the only reason, but part of the architecture of your existence in a way that no other planet in this solar system can claim. Jupiter didn't protect you. Jupiter didn't choose you. Jupiter is not your friend, but Jupiter was the right size. It stopped in the right place. It moved at the right time. And 4.5 billion years later, you stepped outside and looked up at it without knowing any of this. Now you know.